We're now going to discuss California Plumbing Code Chapters 5 and 6, which deal with water heaters and water supply and distribution. Chapter 5 of the California Plumbing Code specifically addresses water heaters. And water heaters are unique in that they are miniature boilers. So there is an explosive component to the pressures that are developed inside. They also have hot water in them, and they are generally fed with fuel gas. So that certainly warrants them having their own chapter within the CPC. You need to verify, obviously, that the materials received are correct, and the water heaters have got to comply with the standards. These are specifically addressed in Table 501.12. And they also, the installation has got to comply with the manufacturer's installation instructions, which we will restate repeatedly throughout these chapters. The product inspector's got to verify that the required clearances are maintained, and the clearances are clearances for combustion, obviously because of fuel gas supply and combustion, and also the servicing and maintenance clearances. And again, we want to reiterate that hot water is defined in Chapter 2 is water that is greater than or equal to 120 degrees Fahrenheit. It is stipulated that water heaters, hot water heaters, must be set to 120 degrees Fahrenheit maximum temperature. Now, with respect to clearances, I want to clarify a couple of things. Clearances are generally divided into two groups, and that is accessible and readily accessible. Accessible means that the accessibility to a component or piece of equipment or an element may require the removal of an access panel or a door or some other similar obstruction. Readily accessible means that a person has direct access to the component or the equipment or the element without having to remove anything. So that's an important distinction to make and to remember throughout this discussion regarding accessibility. The project inspector needs to remember to verify air supply for the water heater. There's basically three types of air supply to consider. Number one is combustion air. That's the air that's required for the combustion process, specifically for fuel gas supplied water heaters. Venting air, that's where the combustion air is actually vented out of the area where combustion takes place. And process air. And process air is about everything else. Process air includes the air required for, say, cooling of appliances, equipment and materials, controlling heating, drying, oxidation, dilution, dew points or humidity, safety exhaust and odor, and also personal safety and comfort are components of process air. The inspector is going to have to verify the seismic anchorage, and seismic anchorage is addressed in section 507.2 and also the health and safety code section 19100. To generalize or to summarize what the seismic anchorage requirements are, the water heater's got to be strapped basically at the top and the bottom third, and the bottom strap has got to be located 4 inches minimum from the controls. DSA's website contains some recommended seismic restraint system designs for water heaters, and these are specifically guidelines for the installation of residential water heaters, which is an unusual concept, but it is what it is. Generally speaking, DSA's guidelines for water heater strapping, seismic bracing of water heaters, is generally accepted in construction to be details which will provide sufficient bracing for water heaters in the event of an anticipated seismic event. Inspectors must verify that the gas connections are appropriate, and we're going to discuss more information relating to fuel gas connections in Chapter 12 of the CPC. The inspectors also got to verify that the operation and maintenance manuals are provided. These are going to be distributed by the contractor to both the project inspector and the owner. It's very important that the project inspector keeps a copy of the O&M manual and verifies that the installation of the water heater complies with the O&M manual. This image of a water heater basically shows the strapping requirements or a strapping requirement for strapping a water heater, protecting it against a seismic event, where you can see there's straps on the top third and on the bottom third, and the bottom third strap either is or is not generally around 4 inches away from the controls located at the bottom of the water heater. You may also remember seeing in the last image that the water heater had a drainage pan located underneath it. The 2016 code was the first requirement, or expressed the first requirement for a drainage pan under a water heater that was installed in the attic area, or an attic ceiling area, a floor ceiling area, or a floor subfloor assembly. The drainage pan is supposed to be 1.5 inches deep minimum, and it's got to have a 3/4 inch diameter minimum drain, which drains to an approved location. There's a conflict that we want to address with respect to appliances located on roofs. Okay, the CPC identifies that fall protection is required if equipment is within 6 feet of a roof edge. However, it's important to understand that this CPC requirement conflicts with the California Building Code, Section 1809A.14, which requires 10 feet clearance from an appliance on a roof. If anything is within 10 feet of a roof, then fall protection must be required. So generally what we'll see is some form of guardrail system set up on the roof edge where a piece of equipment is located within 10 feet of a roof edge. And again, since this particular requirement in CBC is more restrictive, it governs over the more lenient restriction found in CPC. Additionally, buildings that are over 15 feet high must have an interior access to the roof. Now we're going to start discussing Chapter 6 in the CPC, which addresses water supply and distribution. The first component that will be addressed, reviewed, and approved or not by the project inspector is how potable and non-potable water systems are actually identified. This is a very important consideration, especially due to the fact that now non-potable water systems are becoming a little bit more prevalent within buildings due to the water conservation efforts that the state of California has been implementing recently. So the background color and information has got to be sized per the table on 601.3.2. This identification has got to be located at 20 feet on center minimum, and it's important to understand that every pipeline containing potable or non-potable water in a ceiling space or penetrating a room has got to be identified. So if you've got a small closet that's maybe 5 feet by 6 feet, you need to be able to look up and see via the identification on the piping itself exactly what type of water is being distributed in that ceiling space. This identification has got to be visible from the floor. And an important distinction to make between potable and non-potable water is potable water is going to have a green background on the label and include white lettering. Non-potable water will have generally a yellow background with uppercase black lettering that states caution, non-potable water, do not drink. And it's got to include the type of liquid and the flow direction on the label. Alternate water systems are also required, obviously, to be labeled. Alternate water systems are also considered non-potable water, but because of their alternate nature, they are distinguished with a purple background and black uppercase lettering. So for gray water, the lettering or the identification is going to state caution, non-potable gray water, do not drink. For reclaimed or recycled water, the verbiage will state caution, non-potable, reclaimed, recycled water, do not drink. For on-site treated water, the piping label must state caution, on-site treated non-potable water, do not drink. And for rainwater catchment systems, the labeling on that particular piping is required to say caution, non-potable rainwater water, do not drink. One of the primary controls that plumbing system designers must take into account is to ensure that it's impossible to cross-contaminate the potable water supply. This is without question the main priority of the designers for plumbing system design. Generally speaking, some form of backflow prevention device or assembly is required, but the need is determined by the design team as well as the specific design, the installation parameters, the design parameters, and the requirements are ultimately decided by the design team. And they have a lot of options at their disposal based on the information provided in Chapter 6. And the project inspector is going to want to review the approved submittals to verify which type of backflow prevention device has been approved and would be expected to be seen installed on the project. It's important to understand that some installations, based on the climate or the location that the structure is located in, may require some form of freeze protection, whether it's blankets or heat wrap tape or any number of methods to make sure that these generally exposed backflow prevention devices are not going to freeze. Backflow prevention devices are required to be tested at the time of installation or repair or relocation, and these tests are supposed to be required to be performed by a certified backflow prevention tester. These are also supposed to be performed on an annual basis, but that particular requirement falls on the owner. The important thing to remember for a project inspector, again, is to, number one, make sure that the certified backflow prevention tester certification is current at the time of the test they perform, and also retain a copy of the documentation that is prepared by the certified BFP tester. As we mentioned on the previous slide, there are several options for plumbing system designers to use with respect to selecting and installing backflow prevention devices. Table 603.2 addresses approximately 16 different types, and these types vary in important details with respect to applicable standards, degrees of protection, and installation practices. They vary from the simplest, which would be considered an air gap, which we see on equipment such as drinking fountains, dishwashers, even some water closets, to large double check, double detector assemblies such as a Febco 856. These are the giant ones that you generally see outside of buildings, and they're used very typically on systems which employ automatic fire sprinkler systems. So it's important to, for us as project inspectors, to be aware of the use limitations for some of the types that are commonly used by construction crews. Specifically, hose connection vacuum breakers, hose connection backflow preventers, dual check, freeze resistant backflow preventer, wall hydrants, freeze resistant sanitary yard hydrants, etc. It's important to make sure that only these particular devices, these four, are only used for a maximum of 12 hours per 24-hour period. These devices cannot be installed for any more than 12 hours at a time, and that's specifically stipulated in the code. These types are not approved for continuous operation. These two images depict the two ends of the spectrum for backflow prevention. The one on the left being a drinking fountain, where you've essentially got an air gap that is separating the supply from the waste. And on the one on the right is one of the more elaborate backflow prevention assemblies, the double detector, double check type assembly that's used for, say, building supply backflow prevention. This particular image on the left depicts a commonly used construction type backflow prevention device. It's a hose connection vacuum breaker, and this is one of the four that we discussed earlier. Is not approved for continuous pressure and is not approved for use for more than 12 hours in a 24-hour period. And again, this is addressed in table 603.2. This image on the right basically shows just the vacuum breaker itself with a cutaway view, showing a very small diaphragm, spring-loaded diaphragm inside that is meant to prevent backflow of the hose water. However, if we look at the image on the left, there's no question this is a prohibited installation, and you can review the definition for prohibited installation in section 602.1, and it's prohibited even though this is, you could argue it's a temporary installation, for the reason that it's obviously a direct connection between potable water and unused, unclean, polluted, or contaminated water. And there's no way that that small hose connection vacuum breaker will not prevent back siphonage out of that filthy barrel during some sort of catastrophic event. This image here illustrates a typical catastrophic event, and it's as simple as, a utility crew inadvertently compromising a water supply line upstream, or even generally even maybe downstream of the potable water supply for the building, in that as soon as that particular area where the utility crew has poked a hole in the water line, there's going to be a tremendous loss of pressure and a tremendous volume of water that's going to start shooting out of that area. And that loss of pressure is going to suck water from any place that it possibly can. Upstream, downstream, branch lines, main lines, it doesn't matter. And it comes with such tremendous force that there's no way that that small little diaphragm in that hose connection vacuum breaker is going to keep back siphonage from taking place. This picture is simply an illustration which drives home the point that There are some situations where one of the larger backflow prevention devices, similar to what we discussed before, a FEBCO 856 or something of that nature, which is commonly used on water supply systems to buildings. If they're located in a vault, it's extremely important that the designers obviously know first that in the case of these things failing, a tremendous amount of water can be discharged in a very short amount of time. So if they're located in a vault, the vault has got to be designed to allow that water to escape unobstructed from it. And there's also a requirement for 12 inches minimum. You can think of it as an air gap between the bottom discharge on the bottom element in the backflow prevention device to grade. This is another picture of clearly a prohibited connection. You've got, in essence, probably a potable water supply, which is feeding a fire hydrant, and the contractor has connected a hose on the discharge side of the fire hydrant, which is running out of sight into a manhole, which appears to be going into a storm drain. And there's just no telling where the end of that pipe is, and there's just no guarantee with this particular connection that backflow prevention is even being implemented. So this is certainly a prohibited connection and cannot be allowed to be connected. This photograph basically shows a depiction of what can happen under a catastrophic back siphonage event. In this particular situation, this is a 500,000 gallon storage tank of potable water. And you can see how the sidewalls have been deflected in. This was caused from a car running into a fire hydrant that feeds basically this tank. And obviously these tanks are vented, but the vent on the top of the tank certainly wasn't designed to mitigate the chance that a catastrophic release of pressure or a low pressure condition was created, and just allowed water to be sucked out of this tank as quickly as it could be sucked out, and even more so, creating the damage on the outside of the tank that we can see. This is another image that shows the destructive nature of a catastrophic back siphonage. And again, the point is, if water back siphoning out of a main supply line, this very heavy steel line, can create this kind of damage to a structural piping steel water piping line, there's no way that some sort of little vacuum diaphragm within a hose connection vacuum breaker would be able to stop the water from being sucked out of that filthy 55-gallon drum that we viewed on the previous slide. This image shows a typical, an illustration of a vacuum breaker backflow preventer assembly. This particular image shows a reduced pressure principle backflow prevention assembly, and these are required on water supply lines that carry water in excess of 120 degrees or steam. This is a photograph showing a better view of a reduced pressure principle backflow prevention assembly. And again, potable water connections to steam or hot water boilers are required to be protected by this type of backflow preventer or a double check valve backflow prevention assembly in order to comply with the requirement that hot water boilers or steam never comes in contact with the potable water supply. Section 603.5.21 is a new section that addresses chemical dispensing equipment. We might see these at a swimming pool or some other such component that uses chemicals. The important things to remember are that the water supply to the chemical dispenser has got to be protected from backflow, obviously, by one of the following types of backflow preventions, and that is they are an air gap, an atmospheric vacuum breaker, pressure vacuum breaker backflow prevention assembly, spill resistant pressure vacuum breaker, or a reduced pressure principle backflow prevention assembly. So we would expect to see one of these 5 different types of backflow preventers in order to isolate chemicals from the potable water supply. Table 604.1 is a very useful table in verifying what are acceptable products to be used in the distribution of potable water. It's important to review it. There are some restrictions in the footnotes which should be reviewed and understood. Generally speaking, there's an entire variety of acceptable products to use for distribution of potable water. Asbestos cement pipe, brass, copper, CPVC, ductile iron, galvanized steel, polyethylene, PEX, polypropylene, PVC. There's a whole variety of them. So this particular table is extremely important. In section 604.2, the lead content that's permissible to be used in materials for potable water supply are identified and restricted, obviously, as they have been. The same holds true for any type of solder or flux used in a potable water supply system. And the amount of lead that's permitted in non-potable water systems is also identified. 604.10.1 addresses tracer wire, and the reason this is identified as an amendment change with this code cycle is that previously there was a conflict. There was a portion in the California Plumbing Code which identified that 18 gauge tracer wire was acceptable, and that conflicted with other areas that identified that 14 gauge was the minimum tracer wire gauge. So that conflict has been resolved, and it's important to understand that tracer wire for potable water is identified as blue, insulated, 14 gauge minimum copper direct burial. And this wire has got to terminate at each end and be visible at each end. Similar to the previous slide, which identifies materials that are approved for use with potable water supply systems, Section 605 addresses acceptable joints and connections which are permitted for use with potable water systems. The reason that the section numbers are identified in red underlined is because these section numbers changed. However, it's very important to review all of these sections because they identify the specific nuances for all these different types of acceptable joints for water supply distribution. It's also important to understand that, obviously, as we stated previously, that the approved plans and specifications dictate what is approved for use on any given project. The reason I say that is, even though that this type of compression connection that is shown here is acceptable for use, it is possible that it may not be approved for use for any given project. So even though you've got a whole variety of joint types, mechanical joints such as compression, flanged, grooved, pressed, metal insert, press fit, elastomeric gaskets, or other types such as threaded, soldered, brazed, flared, solvent cement, heat fusion, electrofusion, socket fusion, slip, dielectric union. There's many others. And because it's an installation process, the details will probably be identified in the approved specifications. So again, to reiterate, it's extremely important that you use the approved plans as the basis for your inspection for what is compliant for each project for joint connections. One of the joint connections that is not adopted by DSA is located in section 605.10, and it is PEX AL PEX, plastic tubing and joints. You'll see here in this slide that we have added a banner, DSA SS and DSA SS/CC, which reiterates the fact that DSA does not adopt this particular joint connection for use in projects under DSA jurisdiction. And this is not a change. This has always been the case. The table that identifies the different joint connections has always had a footnote that identified the fact that DSA does not adopt PEX AL PEX connections. However, we felt it was important last code cycle to attach a banner to the actual verbiage in the code section itself outside of the table to make this more clear. We've decided, since this is, still only one code cycle old, we're going to go ahead and keep this. We wanted to stress this again. There's some new additions to PVC use, primarily related to the fact that PVC exposed to the environment, specifically sunlight, has got to be protected in some way from ultraviolet damage. So what you see here in section 605.12 is some new language that basically reiterates the fact that any exposed PVC outside has got to be protected from ultraviolet degradation. And there's a couple of methods noted here, either number one, wrapped in 1.02 millimeter thick tape, or otherwise protected, which is an all-encompassing option, which design professionals will suggest options for protection on a case-by-case basis for each of their projects. Section 605.15 addresses dielectric unions, and last code cycle the Division of State Architect decided to go ahead and attach our banner to this particular section, which basically says that dielectric unions must be used at all points of connection where there is a dissimilarity of metals, and that just made complete sense, and we're actually co-adopting that with OSHPD. Section 609 addresses installation testing, unions, and location. And nothing has really changed, but we certainly address it here in this training because it does specifically identify testing. So obviously 12 inches minimum coverage is required below grade or below the frost depth in areas where freezing is a regular occurrence. For sewage and drainage lines and water pipes permitted in a common trench, these particular piping systems are actually permitted in a common trench with the provision that all of the pipes that are used for the sewer and the water transmission are approved, the materials approved for use above ground inside of a building. So when the materials are approved for above ground use inside of a building, sewer and water pipes can be in a common trench and at the same elevation. However, if the materials that are being used are not approved for above ground use inside of a building, then the standard provisions for separating the water from the sewer apply, which is basically the water line has got to be a minimum of 12 inches above the sewer line and offset if they're running parallel. Continuing with installation testing, unions, and location, when water piping is located underneath concrete slabs, of course the code requires certain things be done, and these will obviously be addressed in the plans and specifications, but we'll address them here as well. Ferrous metal piping has got to be wrapped in a protective coating, and field wrapping has got to provide the equivalent protection. So depending on what the joints look like, when the piping is installed under the slab, whatever protective coating is located or adhered to the pipe itself has also got to be continuous after the connections are made. Obviously, approved non-ferrous piping is not required to be wrapped. Copper piping has got to include wrought copper fittings with brazed joints. Typically, type K copper is spec'd out for use underneath building slabs, and it's important to understand the difference between soldering and sweating, obviously. Soldering and brazing. Soldering and sweating is typically identified as a process that takes place using heat that's less than 840 degrees Fahrenheit, and brazing, which is going to be used on type K copper with wrought copper fittings underneath slabs, is identified as using heat that is greater than 840 degrees Fahrenheit, but typically the heat that's used in brazing copper lines is anywhere between 1150 degrees Fahrenheit and 1550 degrees Fahrenheit. It's helpful, and we would suggest that you review ASTM B828, which describes the processes for soldering and brazing in great detail. Continuing with installation and testing protocols for water distribution systems, pressure testing is always required at the completion of all installations, and the testing protocols include basically using water that's at greater than or equal to working pressure. Typically we see 1.5 times the working pressure spec'd out, but again, the approved plans and specifications will verify what the testing parameters are supposed to be. It's also acceptable to use air at 50 psi minimum. Obviously, again, and consistently, you're not permitted to use air for testing plastic piping. The reasons are there's a potential for explosions, and it might be helpful to go ahead and check some YouTube videos. There's YouTube videos which show these catastrophic explosive events when air is used on plastic piping. There is an exception to this use of air on plastic piping, and that's for PEX, polyethylene tubing, or the PERT piping that is sometimes used. These particular plastic piping materials may be tested with air if it's permitted by the manufacturer. So again, it's very important if you see these types of materials installed that you review the manufacturer's installation instructions to verify whether or not air testing is permitted for these lines. The pressure has got to hold for obviously 15 minutes minimum duration, and no leakage is permitted during that time. Another important installation practice is the fact that unions have got to be installed 12 inches max from the equipment that requires servicing, removal, or replacement. And obviously the reason for that is that if equipment needs to be removed for replacement or servicing, unions are going to facilitate the ease with which that can be done. A couple more code required installation processes involve the installation of a control valve, which is installed upstream of the union. Obviously, the reason for this is so that the repairmen or maintenance personnel can actually shut the water supply off to the equipment before they unhook the union. It's also required that Any new or repaired potable water systems must be disinfected, obviously, which generally includes flushing, chlorinating, and then flushing again. And then the subcontractor will test to see the clarity or the cleanliness of the water itself, and if necessary, they'll repeat the process to make sure that the chlorination parameters with which they are required to adhere to are adhered to. Obviously, it's extremely important, again, since these types of things are done by others, that the product inspector obtains and retains the documentation which verifies the pressure testing and also the disinfection of the water lines themselves. And this information will be filed in the appropriate folder in your job file for the project. Another requirement is that domestic hot water, which we've addressed before, is 120 degrees Fahrenheit max. The piping must be insulated. Speaking of insulation, this image on the left-hand side of this particular slide shows something that's not necessarily uncommon. It certainly happens, and it depicts a situation where the plumbing contractor obviously insulated the piping, but the way the piping was attached to the backing or the framing members required them to think that they needed to cut the insulation out away from the backing, which is, or the blocking, which is not acceptable, obviously, and this is something you'd want to be able to look out for and remind the contractor to correct this situation if you observe it. The image on the right is another common occurrence. Again, it basically comes back to the issue relating to who gets to where first. So in this particular situation, you can see that there's some copper water lines that are attached to the blocking or the backing, and they have been relief cut, or excuse me, the blocking or the backing have been relief cut in order to make way for the plumbing pipes. You can see in the foreground there's a copper water pipe, and in the background is a cast iron, either a vent or a waste line. And again, this can be a common occurrence, and it's got to be corrected before the product inspector will sign off for this installation.